Hello, my name is Dan Szumski. I'm an independent scholar. I live in Davis, California. The title of my presentation is The Reversible Thermodynamic Process and Its Place in Physics. In the preceding lecture, I proposed a new understanding of the reversible process and its place in physics, and I identified 4 reversible processes in nature. In this lecture, I will explore the possibility that negentropic thermodynamics might mimic reversible thermodynamic behavior in matter's living state. I'll begin by briefly summarizing the first lecture. The reversible thermodynamic process has 3 defining characteristics. First, it is a physical process. It has at least 2 states, and these are cyclic. Second, because it is a process, it produces a work product. And third, it operates at the very limit of the second law of thermodynamics, where no entropy is produced as a result of its operation. We identified 4 reversible processes in nature. Each of these has a work product that contributes to the stability and the function of our universe. The first is light in a vacuum. It provides for electromagnetic energy transport in space-time. The second is the covalent bond process. It provides for microscale mass aggregation. Third, there is the atomic process. It facilitates microscale mass energy aggregation. And 4, gravity governs mass transport and aggregation at the macro scale. These 4 reversible processes act to counterbalance the great entropy principle. This lecture proposes that the reversible process might have a much broader function in the way that it participates in negentropic thermodynamics. I want you to consider the possibility that within the context of our irreversible world, it might be possible to evolve isolated environments which are separated from the reversible process space where we live and which are suitable for more complex processes that mimic the reversible process. However, I'm getting a little ahead of myself. First, I need to digress to provide you with some needed background from physics and chemistry. This is essential if you are to understand the full complexity of the reversible process. Let's begin. Heat energy exists in 2 domains. The first is contained in what I will call the radiation domain. Its spectral distribution is described very precisely by Max Planck's black-body radiation theory, wherein the independent variables are wavelength and temperature, and the heat described in this way is entirely electromagnetic energy. It is one of the most precise theories in physics, and it had the great honor of first introducing the quantum into physical theory. The radiation domain contains heat's more organized form. The remainder of any system's heat energy is contained in the thermal motion of material particles, or what I will be calling the mass domain. It was Helmholtz's great contribution to physics that radiant heat energy reduces to motion, an understanding that Planck places on a pedestal alongside Maxwell's treatment of light as electromagnetic waves. Boltzmann and Maxwell formalized the theory of thermal motion, describing the temperature-dependent velocity distribution in an ideal gas. Thermal motion is heat's disorganized form. Heat stored in the radiation domain is a much more efficient form of energy, having a much lower entropy than its mass domain equivalent. Thus, heat energy's entropic direction is from the radiation domain into the domain of thermal motion. However, I want to focus your attention for a moment on the heat transitions in the negentropic direction, that where heat energy transitions from the mass domain to the more organized electromagnetic energy in the radiation domain. That this can occur in nature is easily demonstrated by introducing mass domain heat to an object. This might be accomplished by moving it rapidly on another surface to induce friction and its heat of thermal motion. If we at the same time induce the same amount of heat energy transfer by exposing an identical object to radiant heat, the sun for example, and then allow both objects to achieve quasi-equilibrium, the temperature will be the same and indistinguishable in both objects, thereby demonstrating that heat energy moves equally well from the radiation domain to the mass domain as it does in the reverse direction. The direction of heat flow will always depend upon the magnitude of the forcing functions in either or both directions. The same is true of the entropy. Its positive or negative direction is governed by the system's forcing functions, and in this regard, there is nothing unusual about negentropy production in nature, albeit a generally unstable condition. If you want to take any system to a far from equilibrium state and then keep it there, one of two things needs to occur. One, energy must be continually supplied to maintain the negentropic state. Or two, energy has to be supplied to transition the thermodynamics into a far from equilibrium state from which there is no way back to the initial state. This is the case that we will be discussing here. The Belgian theoretician Ilya Prigogine called this transition a dissipative structure. He was awarded the 1977 Nobel Prize in Chemistry for his remarkable theoretical discovery. Now, the reason that I've taken you on this detour into heat theory is because heat energy can exist in both the radiation and the mass domains, and as we have seen, it is qualitatively different in each. It is important that you understand that radiation domain heat is the free energy transferred in all chemical reactions, and the loss of free energy in all chemical processes, and indeed in all irreversible processes, is the fractional loss of radiation domain free energy into thermal motion. Let me repeat that. Radiation domain heat is the free energy transferred in all chemical reactions, and the loss of free energy in all chemical processes, and indeed all irreversible processes, is the fractional loss of radiation domain free energy into thermal motion. One might then ask, is it possible that the absence of free energy loss to thermal motion is a sufficient condition for thermodynamic reversibility? Well, let's call this hypothesis 1. The reversible thermodynamic process is characterized by the absence of thermal motion. If this is a true and sufficient condition, we have severely limited the circumstances suitable for reversible behavior. Indeed, The reversible process has to be limited to purely radiation domain dynamics. Let's provisionally accept this hypothesis and see where it takes us. If we are to understand reversible process complexity, it is essential that we first understand the underlying kinetics. All physical processes can be thought of as existing in both a positive and a negative time frame. We will define positive time as that in which the process evolves in its entropic direction and toward its maximum entropy condition. In a similar manner, negative time is movement away from the maximum entropy condition and toward a more far from equilibrium state. And the circumstance that I want you to take special note of occurs at the very limit of the second law of thermodynamics, the furthest from equilibrium allowed by the laws of physics. This very special place is the exclusive domain of the reversible thermodynamic process. Let me illustrate this with a simple chemical reaction that is well studied redox kinetics, where the forward velocity of the reaction is kf and has the units per time, and the forward velocity of the reaction V sub f is measured in moles fifth per time. However, this is only half of the overall reaction, where V sub b equals K sub b times the hydrogen peroxide concentration, and V sub f divided by V sub b equals K sub b divided by K sub f times the equilibrium concentration ratio. And if we then set V sub f equal to V sub b, making the forward and backward velocities equal, we define the equilibrium constant, where K equilibrium equals 23.1. The positive value of K equilibrium indicates a reaction that is heavily favored in the forward time direction. However, while the forward reaction might dominate, there is a small but still significant reaction in what we see as the backward time direction. In other words, we see a chemical event that results in hydrogen peroxide formation in the forward time direction. But in looking more closely at the process, this is the net event, where a portion of the overall structure occurs in negative time. Because this is the reaction's most probable state and its maximum entropy condition, we will call it the reaction's normal entropic process. Now, in an idealized world, it should be possible to alter this reaction and make the forward or the backward direction more dominant. This can be accomplished by altering either or both velocities to move the reaction away from the normal entropy condition. We might, as illustrated in the example shown here, increase the redox field strength. That is, increase the electron activity in the reaction space and thereby increase the positive time contribution to the overall reaction. Conversely, the free energy term H sub f minus G sub f might be increased, making the backward reaction direction more dominant. But what you really need to understand is that making the positive or negative direction of the reaction more dominant moves the reaction to a less probable state and therefore a lower entropy condition. Let me repeat that. Making the positive or negative direction of the reaction more dominant moves the direction to a less probable state and therefore a lower entropy condition. In his wonderful book, What is Life?, Erwin Schrödinger tells us that we have moved our chemical process in the negative entropy direction, or more simply, that it has become a negentropic process, a process where the net reaction velocity departs from the normal entropic process and the process space becomes more organized. And if, as Prigogine tells us, this far from equilibrium condition then branches to a new thermodynamic state that precludes its return to its former entropic state, we have witnessed a dissipative structure, and the world has become slightly more organized than it had been. Now I want you to look at what happens when we take the negentropic process to its limit, allowing either the forward or backward reaction rates to go to zero. This special case places the process at the very limit of what the second law allows. Entropy production ceases, and the process has only one outcome. Do you see how the probability of forming hydrogen peroxide is now identically 1.0? This is the very special case in physics known as the reversible process. I want you to take special note of the way that the concentrations, the probabilities shown in brackets, now transition to specific molecules without brackets. They are no longer concentrations. This discussion illustrates the spectrum of possible thermodynamic states for the hydrogen peroxide reaction. However, while the transitions between the entropic process and the negentropic process can readily occur in nature, the reversible process state does not occur as a transition from the negentropic state, but rather as an entirely independent transition from the entropic state to the reversible process state. However, and this is important, it is possible to put enough energy into a system to move it to this extreme, far from equilibrium, reversible process state. And as we will see in a moment, living systems accomplish this unlikely transition. To understand how this happens, we need to understand the meaning of the free energy term G sub F minus H sub F. In the free energy expression H sub F minus G sub F is the system's Gibbs free energy, and H sub F is the system's Helmholtz free energy, and the former is a subset of the latter. In particular, the Gibbs free energy is the energy that we associate with chemical bonds, and it is entirely electromagnetic energy, or in this presentation's notation, radiation domain energy. The Helmholtz free energy, on the other hand, is the sum of the Gibbs free energy and the system's other free energy component, its molecule's kinetic energy. In most chemical reactions, the Helmholtz free energy does not change, and the Gibbs free energy change is a fractional transference of radiation domain energy to kinetic energy, and thus a change in how the Helmholtz free energy is partitioned between the radiation and mass domains. I want you to understand that the Helmholtz free energy is generally a constant, and in chemical reactions, the change in free energy is always in delta G sub F, where delta G sub F is the radiation domain energy that is lost to the chemical system and shows up as an increase in the system's kinetic energy, and delta G sub F divided by T is the corresponding entropy increase, and it is a positive number. In the reversible thermodynamic process, G sub F minus H sub F is identically zero. There is no mass domain change, and therefore no kinetic energy at all in the reaction space, and thus the entropy, delta G sub F divided by T, is identically zero. You also need to understand how event probabilities differ from the reversible and the irreversible processes. In the hydrogen peroxide example, we have designated the intensity of each chemical constituent as a molar concentration in brackets. H plus in brackets, for example, H plus in brackets, for example. This is in reality the probability of a hydrogen ion in the overall reaction space. For example, at pH 7, the molar concentration of hydrogen ions is 10 to the minus 7th, and the probability of a hydrogen ion in a 1 molar solution is 10 to the minus 7. By contrast, at the limit of the second law of thermodynamics, the probability of all of the aqueous molecules transitions to 1, and the free energy term G sub F minus H sub F becomes identically 0. So, 1, what makes the reversible process so different? And 2, what mechanism makes these unusual probabilities possible? A probability of exactly 1 can exist in an absolutely pure phase. Think pure oxygen. However, in pure water, it is not possible because water contains the water's dissociation products and other very minor constituents. Well, if this is so, is it possible to achieve a reversible process state in the aqueous environment? And the answer is a conditional yes. Let me show you the kind of mechanism that the reversible process would require. My example is taken from some work in theoretical biology, where I envisioned an enzyme having a single zinc atom at its active site and 4 histidine groups in its immediate vicinity. In this enzyme-mediated reaction, an oxygen molecule is drawn into the active site by electrostatic attraction, where it cleaves to the enzyme's active site, forming zinc peroxide. I want you to pay particular attention to the energy flow during this part of the enzymatic reaction. The oxygen molecule in its aqueous environment had a kinetic energy of 1/2 mv squared in a deterministic sense, and kBt in a statistical mechanical sense. However, at the moment that the oxygen molecule cleaves to the zinc atom, its kinetic energy goes to exactly 0. The oxygen molecule's kinetic energy has been quieted. The first law tells us that this energy is not lost. It becomes part of the enzyme-oxygen complex, where it can, for example, contribute to the activation energy that the enzyme imparts to its biochemical reaction. That energy might, for example, result in conformational changes in the enzyme's condensed globular form. But the reason that I have taken you down this path is to show you how the probability of the individual reactants becomes identically 1. Let us assume for a moment that the enzyme's activation energy causes a conformational change in the His groups surrounding the active site that then places their reactive hydrogens in close proximity to the O2 molecule to form hydrogen peroxide. What I want you to see is how all of the mass particles participating in this hydrogen peroxide formation reaction are bound in a way that their kinetic energy is identically 0. And because of this, the probability of each reactant is exactly 1. In other words, this chemical reaction has become exact and precise, 2 characteristics that all reversible processes have in common. Let me explain that. Exact means that when molecules H plus and O2 combine to form H2O2. We really mean that a specific hydrogen ion combines with another very specific oxygen molecule to form a very specific product molecule, hydrogen peroxide. There are no most probable concentrations of H plus O2 or H2O2. There is exactly one molecule of H2O2 created from the other two molecules. Precise means that the reactions occurring within the cell's reversible thermodynamic space are always and everywhere exactly deterministic. There is no Heisenberg uncertainty and indeed no uncertainty of any kind. In fact, the probabilistic rules of quantum mechanics are incompatible with the reversible process. Likewise, statistical mechanical rules that characterize aqueous chemistry are not appropriate here. Everything is exactly deterministic. And I want you to know why this is important here. In the absence of this kind of precision, entropy production, which is uncertainty, ensues. And uncertainty is not permitted in the physics of reversible processes. We have now seen how the reversible process produces a far from equilibrium product, but we haven't yet said anything about how that state becomes stable. The basic concept needed to address the issue was first articulated by Ilya Prigogine, who introduced dissipative structures into physical theory. A dissipative structure is a branch from one far from equilibrium state to another far from equilibrium condition from which there is no return to the initial state. This occurs primarily because the new state is stable. Let me demonstrate a dissipative structure using the covalent bond as an example. Imagine an enzyme cleaving its two reactants that are brought into close proximity through electrostatic attraction, and in this process forming a covalent bond and a new stable chemical quantity. Do you see how two electrons are required by the hydrogen peroxide reaction? I also want you to recall that the negentropic direction occurred because a forcing function caused the chemical reaction to move to a far from equilibrium state. Let me introduce that forcing function. In this instance, it is the increase in the redox field strength of the aqueous solution that increases its Nernst potential, and with it, the availability of isolated electrons. H2O2 formation is the far from equilibrium state from which there is no return to the individual reactants. According to this viewpoint, the enzyme's activation energy has its source in harvested thermal motion. Now look at how the dissipative structure has facilitated the new stable state. The branch to a new stable thermodynamic state is covalent bond formation, from which there is no pathway back to the separate enzyme substrate states. This is a new, but not unreasonable way of looking at enzyme-mediated reactions. We are allowing nature to act exactly opposite to the normal direction specified by the second law. Whereas it is normal that the more organized electromagnetic energy decays into the energy of random motion, the process that we are describing here, and this is important, takes the raw thermal energy of molecular motion and converts it into the very structured electromagnetic energy within the covalent bond. The reversible process is the only place in physics where kinetic energy can be resolved to electromagnetic chemical bond energy. The only constraints in this circumstance are 1. The conversion must be 100%, and 2. it must satisfy the principle of least action. It is my view that the scientific importance of the reversible process lies beyond the circumstances already described. This is because all reversible processes, regardless of their nature, have one additional constraint that bestows upon them their very special place in physics. It is the principle of least action, and what makes it so indispensable is the precision with which it specifies from among all of the possible next steps that the reversible process can evolve to, the one next step that results in the least action. And if the process remains in its reversible state after that step, there is again only one next step that the process can evolve to, and it too is determined by the principle of least action. In this way, and this is important, we see how the process that remains in a reversible thermodynamic state must trace out a very special temporal evolution that we might refer to as the least action process. And as long as the process evolves within the framework of reversible thermodynamics, every next step is precisely determined by the least action principle, and at least in theory, its complete temporal evolution is precisely deterministic. Do you see this dynamic in the covalent bond, where every next step there is only one least action step in play, and it is cyclic? Similarly, the atom's nucleus and its internal wave functions are maintained by a repetitive reversible process. In the next part of this lecture, we will see the living cell as a least action process, but one that is not endlessly repetitive. As we wander deeper into the nature of the negentropic process that mimics reversibility, it is only natural that we wonder about life's negentropic state and its relationship to reversible thermodynamic behavior. This discussion needs to begin by asserting that matter's living state is not a reversible thermodynamic process. Life produces entropy and requires continued refueling. Instead, it is a negentropic process where its forcing function produces reversible process outcomes because its chemistry continually is driven to a more stable, far from equilibrium condition. It achieves this far from equilibrium state by maintaining a continual influx of redox field energy into the cell. Its far from equilibrium condition is made stable by dissipative structure transformations involving covalent bond formation that traps the negenentropy condition in covalent bonds, thereby preventing a return to its prior unbound state. Nevertheless, matter's living state does involve elements that are truly reversible, specifically its covalent bond formation. In Table 1, I compare some intrinsic properties of the solid, liquid, and gas states to matter's living state. I want you to better understand what makes the living state so different. The comparison illustrates how a redistribution of energy density within the mass and radiation domains is responsible for the phase transitions between solid, liquid, and gas states. The living state extends this pattern by storing the increasingly large amounts of radiation domain energy into covalent bonds, and in so doing makes life's very far from equilibrium state stable. The table also shows another important difference. Matter's solid, liquid, and gas states are all maximum entropy states that have a probability of exactly 1. This means that their state is highly probable, and in fact it is the most probable state. The living state is fundamentally different, having a probability of about 0. Or to say it another way, the living state is matter's most improbable state. Shannon and Weaver would say that its information density is higher than in any other state of matter. But I want you to understand that although life's template is stored in its DNA, RNA molecules, this represents only a very small fraction of the cell's total information content. From the first synthesis step following mitosis, each new covalent bond captures 1 bit of information, and these bits are cumulative until the next cell division occurs. But the cell's total information content is even greater. Do you remember how the principle of thermal quiescence quieted the enzyme's substrate molecules, and how conformational changes in the His groups were the repetitive steps in enzyme formation? Each of these non-structural steps also contributes to the cell's information content. This can be seen in the way that the enzyme's amino acid chain is useless until it undergoes all of the conformational changes that are required to bring it into its active globular form. I also want you to see how the evolution of the cell's information is always directed forward in the negative time direction, or in the direction that always produces more information than existed at the previous time step. And finally, I want you to understand how the principle of least action provides the perfect template for life's synthesis pathways. The least action process is sequential. Each step occurs only after the previous step is completed. This sequence of negentropy steps is facilitated by the cell's continuing increased redox field strength, and because each step takes place in a reversible process space, it is exactly deterministic and very precise in its outcome. Whereas the covalent bond example is a repetitive process where at each next step there is only one possibility for the next process step, in living systems there are innumerable biochemical steps that can occur next. However, the living state alone has a least action process paired with a DNA template that continually guides its least action process along a synthesis pathway where each next step evolves toward a complex and very specific work product. This kind of biological self-organization is brought together in a process that requires 3 elements. First, a bounded reversible thermodynamic process space, the interior of the cell membrane. Second, a forcing function, the continual influx of redox field energy. And finally, a synthesis template, the DNA molecule. conclusion, this lecture's description of the reversible thermodynamic process is in sharp contrast with the current paradigm in physics. It holds that reversible processes are everywhere in nature and are at their most fundamental level responsible for the stability and the order that exists in the material world, including living systems. This thesis is justified from classical arguments and contemporary understandings drawn from physics, chemistry, and biology. It doesn't change reversible thermodynamic theory in any way, but it does clarify the subject matter by eliminating its abstract quality and possibly identifying 4 examples in the natural world. Neither the covalent bond nor the atom's nucleus were known when the classical understanding of reversibility was formulated. This manner of rediscovery in the sciences should be an essential element of academic lectures. Science is a dynamic and holistic discipline where new experimental work or theoretical insights from any of the disciplines might integrate into and alter any of the others. Aside from the 3 laws of thermodynamics, Maxwell's equations, and the atomic theory of matter, there are only a handful of other subjects. There is very little in science that is absolute. Academic lectures should reflect this reality by acknowledging the shortcomings of today's understandings and encouraging independent scholarship and outside-of-the-box thinking. I want to thank you for your attention. The references are included at the conclusion of this lecture.